Good afternoon. Shortly, we will hear an interesting lecture by Dr. Tal David on quantum science and technology. This is part of a webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will be delivered to your mail. My name is Shlomo Glaser. I am the manager of Photonics Israel. With your permission, few words in Hebrew. בשנים האחרונות התפתחות מהירה בפיזיקה קוונטית ויישומיה. הפיזיקה הקוונטית מסבירה תופעות שאינן מוסברות על ידי הקלאסית ושאינן ניתנות לחיזוי על ידה, אבל ניתנות למדידה. והיא מהווה פתח עצום ליישומים רבים. היא מייצרת נדבכים נוספים לפיזיקה הקלאסית, והשימוש בה ידרוש מאיתנו התאמה של האינטואיציה ההנדסית. היישומים הם במגוון תחומים. במחשוב, בתקשורת, בניווט, גלאים, מדעי תאוצה ועוד. עבורם יהיה צורך במהנדסים בעלי ידע מתאים. הטכנולוגיה הקוונטית מתפתחת בקצב מהיר. יש צורך בהעשרה מתמדת של הידע. זו מגמה עם פוטנציאל כלכלי רב ומייצרת הזדמנויות לתעסוקה והתפתחות אישית. אז בואו נלמד. עכשיו אנחנו פותחים סדרה של 4 הרצאות, אבל אנחנו נביא עוד הרצאות שיתעסקו בצד היישומי. בואו נרכוש ונשביח את הידע, וכך נוכל להיות מוכנים לניצול ההזדמנות שהטכנולוגיה הזאת מזמנת. אנחנו בסוף ההרצאה הזאת וגם בהרצאות האחרות, אנחנו נבקש משוב מכיוונכם, וגם הכוונה במידה ואתם מבקשים לשמוע הרצאות על מרכיבים נוספים בפיזיקה ובטכנולוגיה הקוונטית. דוקטור טל דוד is a quantum physicist with experience in academia, industry and government. Dr. David heading the Israel National Quantum Initiative on behalf of several government R&D agency. Dr. David, the floor is yours.
Okay, thank you very much, Shlomo. I'll share my screen. And thank you for having me and inviting me. I think it's an excellent initiative by Photonics Israel to bring the field of quantum science and technology to the engineering community in general. As you'll see in my presentation, this is very much in line with what we are doing in the next few years in Israel. So I'm pleased to speak before you today. As Shlomo said, the National Quantum Initiative in Israel, which I'm heading, is a joint venture of what is known as the Telem Forum. That's the Forum for National Research and Development of Infrastructure, usually. And this is comprised of the Innovation Authority, the Planning and Budgeting Committee in the Council of Higher Education, VATAT, the Directorate for Defense Research and Development in the Ministry of Defense, also known as MAFAT, the Ministry of Science, and the Ministry of Finance. So in the next, half an hour, 40 minutes, I will speak a little bit about what quantum science and technology is and give a few examples, mostly from the industry. I think that will be the more interesting topic for the audience today. And also I'll say a few words about our initiative, how it came to be, and what are the principles and components and so on. As in every webinar, we have a chat window that you can write questions, and after I finish, Shlomo will moderate a few questions and answers. I hope that I'll be able to give you good answers. So let's start. Okay, so quantum science and technology is not a new thing. It's been around for about 100 years, and we can separate that into 3 periods of time on the timeline. About 100 years ago was the definition and discovery of quantum theory and the principles. Then there is what is now called as the first quantum revolution in technology in the 1950s, 60s, with the invention of masers, lasers, transistors, and so on, typically characterized as, macroscopic phenomena or ensemble phenomena of quantum properties or principles. And today, in the last few years, we are in a stage that is called the second quantum revolution. And the idea there is to go into more sophisticated, more advanced uses of these quantum principles that you see here, a few of them in the middle, really at the single quanta level, the single atom level, single photon level, and so on. And so in quantum science and technology, we take these principles or phenomena from quantum theory, and from them develop components or systems or devices or services that have a tremendous impact, or in some cases will have a tremendous impact on very large number of areas or fields, from smart transportation, the energy market, materials and drug development, defense applications, the finance market, and so on and so forth. This is a slide that I always show, and every time I need to update it again, showing some of the national initiatives around the world by governments. The numbers here are very rough estimates in millions of dollars, typically over 5-year periods, but in some cases it's a little bit different. So don't take these numbers really too much precisely. The last ones that have increased their participation in the race is Germany, that on top of everything that it did for the last few years with the European flagship program, in the last summer, they have declared that as part of their economy boost package due to the COVID-19 crisis, they will invest 50 billion euros in economic growth mechanisms, and some of them are technological ones. And among them is an investment, or an additional investment actually, by Germany in quantum information and quantum technology of about 2 billion euros over the next 4 years. The US has also, they joined, already increased a few times the size of their program, and the number that's listed here is only in the civilian side. They also have a defense sector program, which the numbers are not publicly released, but they are acknowledged and known to be quite large as well. And before them, also within the last year, India has declared that it will invest over $1 billion in the next few years in quantum technology. And all the time we see more and more governmental initiatives, small and large, small countries and large countries all around the world. But we don't see only governmental initiatives. We also see more and more commercial corporations and companies entering this field. So I guess that most of you have already heard in some instances about the IBM and Google quantum computing projects, but they are really not alone. There are many other companies, both in quantum computing and also in other fields like quantum sensing, quantum communication, and so on. So this is a very not incomprehensive list of some of the corporations that are working today. So you see companies that are really focusing on specifically that, and companies that come and want to utilize the advantages that we'll describe shortly of this field. For example, in finance, so you have companies like Citibank or JP Morgan Chase that are in this field. In the automotive industry, you see Volkswagen and Daimler, and so on and so forth. So looking at the quantum science and technology from the application point of view, typically you can separate it into 3 main application vectors. These are not, the only ones, but these are the typical ones that people are speaking about. The first one is precision measurement or quantum sensing. The idea there is that we take the principle of quantization, that you have a discrete set of states that quantum systems can be found at. And this energy level spectrum that you see, for example, in atoms, is depending on very basic fundamental physical parameters. And this leads to an ability to measure very, very precisely all sorts of things. For example, we can measure time and frequency with quantum or atomic clocks. We can measure fields like magnetic fields, like gravitational fields. We can measure forces like inertial forces, and so on and so forth. So this is one component. The second component is quantum communication, which typically, as we'll talk about in a little bit, is mostly quantum key distribution or quantum cryptography. But we're already seeing now people going beyond that, speaking about the quantum internet or quantum networks. The idea there is to take advantage of the fact that due to the uncertainty principle and the measurement principle of quantum theory, one can show that you cannot clone a quantum state without leaving some trace behind to what you did. And this is the basis for a cryptography channel to pass secret keys or information in a physically secure manner, as opposed to most public key distribution protocols that rely mostly on mathematical complexity these days. And thirdly, there's the field of quantum information processing or quantum computing in simulations, which receives possibly the biggest buzz. And the idea there is to take advantage of quantum superposition principles, quantum entanglement, and quantum interference in order to be able to realize some computational tasks in a very efficient way, sort of a parallel computing paradigm, which will, I think, shake the world, and we are already starting to see some examples for that. Putting these three vectors on a very qualitative, not quantitative at all, plot of maturity versus time. So we see that the vector of quantum sensing is the more mature one. It's been here for quite some time. Atomic clocks have been here for decades, and they are getting more and more used. We'll see in some of the examples the main vectors of research and development in this field in the next slides. But it's not only clocks, it's inertial sensors for navigation, it's quantum imaging for material and medical applications, and so on and so forth. The field of quantum cryptography or quantum communication is lagging a bit behind in terms of maturity, but already there we're seeing commercial use, we're seeing products being sold, we see about 1,000 patents in that field around the world, and we see quantum communication networks being deployed in many countries, in the US, in Europe, in Japan, Korea, Russia, and China, of course, as we'll see in the next slides. And then quantum computing and simulation is the least mature one, but it's the one that's getting the most attention, both in scientific progress and also in the industry and investments. So usually when people talk about quantum computing, they are talking about the uses of code breaking, Shor's algorithm that was discovered in the mid-90s. But this is probably the farthest away application that we envision right now. But what we already see starting to have demonstrations and impact is problems in optimization problems like material design, like drug development, and so on. And a little bit into the future, we're talking about applications in quantum machine learning or quantum AI, and so on and so forth. So that was the point of view of the applications, but another point of view that we can take to look at quantum science and technology is the physical platforms that we actually use to realize these systems. So what are the building blocks? What are we playing with? So in order to get access to the quantum phenomena or principle, we need to go to, typically we need to go to very small length scales or size scales. So typically we see either atomic systems, they can be atoms that are at room temperature or a little bit elevated temperature. They could be atoms that are cooled down to a millionth and even billionths of a degree above absolute zero using lasers and magnetic fields and so on, or lasers, yeah. These atoms could be either neutral, they could also be charged atoms or ions, typically that you see in the very high-end sensing applications or in quantum information. You can also see a bunch of other platforms that I do not do them justice by putting them all under a title called artificial atoms, but the idea there is that an assortment of platforms that are solid state, but they are engineered to behave like atomic systems with the energy level structures and so on. So among these, you could count quantum dots, you could count color centers in diamonds or in other materials. You can mention superconducting circuits or Josephson junctions in superconducting and so on. And finally, we also have quantum technology that is done on with photons. And when I'm speaking today about quantum technology with photons, usually I'm talking about single photon physics or few photon physics, and not a huge ensemble of photons like you have in lasers. So truly, a laser is a quantum device, but it's been here for a long time. It's evolved into its own discipline. So it's become a separate thing. And right now, usually when you talk to quantum technology people, you're discussing single photon physics or few photon physics. So these are the building blocks that we use to access the phenomena of quantum technology. And of course, around all of this, there is a periphery of how to initialize these systems, how to read out, how to control, how to extend the performance, and so on. So in the next 3 slides, I'll give examples a bit from the world, and then we'll see a few examples from Israel as well, of applications of each of these 3 vectors. So this slide shows a few examples from the world on quantum sensing technologies. So on the top left here, you could see the American chip-scale atomic clock. This is a project that was initiated by DARPA in the US, invested over $150 million in the development. It's already matured and went into the industry, and it's now selling thousands of clocks per quarter. The idea of this clock is that it is low power, it's relatively low cost, and it's basically expendable. The basic idea of a clock is that you have some cell that's holding atoms, and we're probing the internal structure of the atoms. So the energy level is separation between 2 levels of frequency through the Planck's constant. And if we measure the internal structure, we measure the frequency, and the atom behaves like the pendulum of a clock. And we can close control loops and stabilize our clock according to that pendulum, to that frequency of the atomic clocks. And these are the most accurate clocks, typically by orders of magnitude, relative to what you're used to with your quartz clocks in your phones or in your watches. But this is not the most accurate clocks. These are, this product goes to the low cost, low power market. And this cartoon shows a use for such clocks where you have a ship that's, transmitting some seismic or acoustic wave into the ocean and underground, underneath the sea. And you have an array of microphones or geophones here, and each of them has this small clock, and they get and sample the returning waves and understand the internal structure of the ground beneath the ocean. And this is used for the geophysical exploration market to understand where you have deposits of oil or gas or minerals and other stuff. On the bottom right here, we see a very similar device, a little bit larger. This is a quantum magnetometer or magnetic sensor. It works very similarly to an atomic clock, but this time, instead of measuring only the internal structure of the atoms, we are using energy levels in the atoms that are responding or sensitive to external variation of magnetic fields. This is also used in the world, for example, in this company, Geometrics, for geophysical exploration as well. And you also have other applications for that. On the top right here, you see a little bit more sophisticated device from Northrop Grumman. You can also see the size of it. This is a miniature gyroscope. that is, again, working on the interaction of light with atoms, measuring, it's like a magnetic gyroscope. So we're measuring not only the magnetic field, but also the rotation. The rotation could be the rotation of the Earth, but it could also be the rotation of some platform that this gyroscope is positioned on. And this small gyroscope, already in the first proof of principle demonstration by Northrop Grumman about 6 or 7 years ago, went beyond the best gyroscopes that you typically find in the industry today, and this is only the beginning. On the left-hand side, we see a little bit of a different device, a little bit larger than the clock or magnetometer or the gyro. And the difference is that the previous examples that I gave, they all use atoms that are at room temperature or above room temperature, let's say 100 degrees centigrade or something like this. And their performance is limited by the fact that because they are in elevated temperatures, and according to a Maxwell-Boltzmann distribution, each atom has a little bit different temperature or a little bit different velocity, and therefore, in its interaction with the laser light that is used to initialize it and also to read out the state of the atoms, there is the Doppler effect that causes a smearing of the signal and a limitation to the sensitivity. What we have on the left-hand side here at the bottom is a cold atom device from a company called AOSense in the States. That's a spin-off from Stanford University. And this is measuring gravity at a nano G level. So that's 1 billionth of G that we learned from Newton, that is about 9.8 meters per second square. And the difference between cold atoms and hot atoms is that because atoms are very cold, it means that they have very little kinetic energy, or the velocity is very, very much slowed down. And therefore, the Doppler effect it becomes very much insignificant, and we can go further beyond. So this is an example also used in geophysical exploration. And according to unofficial sources, the US Navy has employed such sensors in its submarine vessels in the Navy for navigation. But this is unofficial, so I cannot confirm it. The second vector that we've seen before is quantum communication or quantum cryptography. And the clear leaders here are the Chinese, that already a few years ago have invested huge amounts of effort in building capabilities. One of these capabilities is ground-based systems. So on the right-hand side, you see a line-based, it started as a test bed, but today it's not a test bed anymore. It's a real project that serves the financial and the banking industry in China. It's a 2,000-kilometer landline based on optical fibers, made of a few tens of segments because of limitations on how much you can push these photons along the optical fibers, because as we said before, you cannot generate copies or clone these quantum states without affecting them. So you cannot use, typical fiber amplifiers. So for now, they're working in segments and build these lines. And also at the two edges, you see local area networks that are working on a smaller scale of distances. So this is an amazing project that's being active for a number of years now. And also on the left, you could see, sorry, a project that was launched about 4 years ago of the first demonstration of quantum key distribution or quantum cryptography via satellite. This is still a scientific experiment. It's not something that is commercial, and the rates of secret key generation there are very slow, but it's progressing very rapidly. And today there is a real race between about 10 projects from different nations around the world on who will be the next one to put a quantum satellite in space that will actually be practical and useful for commercial use. I think the closest ones are the people from Singapore that have already launched a quantum satellite into space, but they have not completed, the complete quantum key distribution protocol between Earth and that satellite, but they're progressing very rapidly about this. Third example is about quantum computing. So people hear about quantum computing very much, and you'll have lectures on this in the next lectures in the series, as Shlomo said in the beginning. And right now we are at the edge of what is called quantum supremacy. And this is the point that we can see that quantum computers are capable enough to perform some algorithms or solve some computational programs that normal or classical computers cannot do in any reasonable time, even high-performance computers or supercomputers. So we are right on the verge of that. A few things to note about this is, for example, IBM has launched a few years ago already a cloud service that everyone from their home can access the IBM quantum computer via the cloud and get familiar with it and play with it. So some of it is already available free, and some of it is available on paid programs, and they are continuously progressing. They have already established something that looks like a Moore's law, for a figure of merit that's called the quantum volume. It encompasses together the number of qubits and the quality of qubits or quantum bits in the computer. Right now, the best one that they have is a computer that has 65 qubits that was announced just a couple of months ago. And they also, in the last few weeks, released a roadmap of reaching in about 3 years or a little bit over 3 years, 1,000 qubit computer, very ambitious task. And the important thing about this cloud platform is that it enabled hundreds of thousands of users to work on a quantum computer that they do not hold and do not need to develop themselves to some extent. And this is amazing. They developed an ecosystem of users and entities that are trying to see what quantum computing can bring to the table. This is exciting. Second thing to note is that I think over 6 months ago already or more, Google claimed to show quantum supremacy. They took a mathematical problem of some probability distribution sampling and showed that on the Google quantum computer, it took them about 3 minutes to solve. And they showed that doing the same problem on the best high-performance computer that Google has will take 10,000 years. This started a debate between IBM and Google of what's the best way to operate a high-performance computer, and if this thing needs to be solved over 10,000 years or maybe faster, but it doesn't really matter. The important thing is that we show that really we are on the edge of beating or overcoming the line that quantum computers can do stuff that classical computers can no longer do. It actually also creates interesting problems of how you validate the solutions that quantum computers will be giving us, and that's very interesting problems that people are tackling that. We also see initial demonstrations of algorithms. For example, Volkswagen about 1.5 years ago, I think already partnered with D-Wave. That's a Canadian company that are developing quantum simulators or analog quantum computers, if you like, to solve optimization problems. And they have shown the ability, for example, to solve the optimization problem of traffic management in a city in order to minimize traffic jams, a thing that has a tremendous financial or economic impact. And they've shown a few orders of magnitude, I think about 7 orders of magnitude improvement relative to what the best classical algorithms are showing today. And this is something that is very interesting as well. Narrowing down to Israel, what we have in our local area. So in the academy, on the left-hand side, all the universities in Israel today have quantum science and technology centers, I think, except one. These centers bring researchers together, mostly from physics and computer science, but not only that. You see more and more engineering going into that. You see people from chemistry, from math, from biology, even from philosophy and from law studies that are taking a look at quantum science and technology. The academic community in Israel is considered very good in quantitative academic parameters like citations or H-index or number of European Research Council grants and so on. It's also considered a relatively young community, but it's quite small. We have between 100 and 120, maybe a little bit more than that by now, research groups in quantum science and technology today, and this is one of the big challenges, as I'll speak about a little bit later. On the industry side, we have also not many, but this is growing. I'll talk about that in the next slide. And in the government sector, the leading entity that has a dedicated quantum science and technology portfolio is MAFAT in the Ministry of Defense. It is not to say that the other R&D agencies in Israel have not invested in quantum. They certainly did that, but not in a dedicated portfolio. And this is changing now in the national initiatives where we're all joining forces. So a little bit about the industry map, and I'll give a few examples of, from the industry. I think we have time for that. When we established the national initiative just about 2-3 years ago, when we worked about how to establish it, we counted about 3 or 4 industrial groups or companies involved in quantum science and technology in Israel. And right now, as you see, we're counting about 25 companies. Some of them are under the radar. So these are the 3 little dots here. Some of them are big companies like the defense establishment, Rafael, Rafael, Elbit, IAI, and so on. Some of them are large companies like Mellanox. Some of them are medium-sized companies like Accubit making atomic clocks, and we'll see example for some of these in the next slide. And some of these are startups. We also see that we have companies working on the hardware in quantum technology. Some of them are working software, mostly in quantum computing, including IBM, Haifa, which are part of the global IBM project. And we also see some component and materials manufacturers that are moving into quantum, people that have been active. Certainly people from photonics know, for example, Raycall or Opsys from the photonics area, so they're moving into the quantum area. So let me give a few examples from the industry. So for example, Rafael has 2 centers of excellence, one that is focused on the more physical scientific aspects of metrology, for example, for timing and navigation, working with cold atoms, with hot atoms, with anti-centers in diamond, and so on. The second center of excellence from Rafael is involved in miniature quantum devices. So together with Accubit, for example, they have partnered to make the analog of the chip-scale atomic clock in the Israeli version, as we'll see, I think, in the next slide. And of course, all of this is under the big backbone of Rafael as a big integrator for many defense applications. Accubit is a small company, about 50 people. It's not very new. They're over 20 years old, so they're not a startup anymore, but they're small, and they're the only company in Israel working on atomic clocks and fighting in a very competitive market. Atomic clocks are the most used device in real applications. You can see them in transportation, in radar technology, in communication, in synchronization, in navigation, in command and control applications, in both the civilian and in the military arenas. And the current research and development trends, as you could see on the top right here, is the first generation of the chip-scale atomic clock from Accubit that's already in the market. And right now they're working on a very similar device, MEMS-based, like the American one, a little bit better in some parameters, that is in advanced R&D stages. But as we've seen before, these clocks, they're very good. They have a microsecond per day drift or so, but they're not the best ones. We're also working in Accubit on compact primary clocks. These are clocks that are based on cold atoms at the nanosecond per day drift level. And this is still under development to get them to a stage that you don't need a big room to hold this technology, but something that will be an engineering like 19-inch rack grade, like the old cesium clocks that some of you may be aware of. Also, there's a matter of time and frequency dissemination. Today, a big motivation for atomic clocks is the fact that we cannot rely on GPS anymore. This is true certainly for defense applications, but it's also true in the civilian applications. For example, autonomous vehicles that are moving around in urban environments cannot suffer from, a block of the GPS signals or jamming or spoofing of GPS signals in urban scenarios, and they need quite a high demand of timing requirements for operation and for communication. So there's a matter of time and frequency dissemination from good clocks to the low-cost clocks. This is an interesting vector as well, and this is also done in Accubit. The Israel Aerospace Industries, the ELTA division, is working on quantum magnetic sensing, as we've seen from the company Geometrics before. So this is a similar project, but relevant more to the defense area, working really from the basic components of how you bring the atoms and hold them and control them to big homeland security systems that employ many such magnetometers. Just to give you a sense, the world record in quantum magnetometry sensitivity is held by a dear friend of ours from Princeton University, Professor Amalis. They got to sub-femtotesla sensitivity. And for those of you who are not really familiar in magnetic field units, this is about 10 orders of magnitude beneath the level of the magnetic field of the Earth. Or if you would say, like to take it, for example, for the medical area, this is about the magnitude of the field that is emerging from the brain, wherein one neuron is firing in the brain, creating current that leads to a magnetic field. So these are really accurate sensors. Quantum Machines is a young startup, considered to be the first Israeli quantum computing company, already selling around the world. And what they are developing is not the qubits themselves, but the next level up in the stack of a quantum computer that is the controller that actually speaks to the qubits, controls them, initiates the pulse and readout from what the actual atoms or qubits are doing, and also connecting to the higher levels of the stack. So it's a whole platform, including basic computer language and so on, working very nicely and growing very rapidly. Involves both with research market and also with around the world, a cool company. Another startup, even younger, is called Classic. So if in the stack that we see here in the cartoon, you have the qubits at the bottom of the stack that IBM or Honeywell, Intel, or Google are manufacturing, and quantum machines that I mentioned in the previous slide are working on the next level of quantum control. So Classic are at the, probably the highest level of the quantum computing stack, working on quantum software, or more accurately, they are developing computer-aided design tools for quantum algorithms. So you have a problem, you want to formalize it into the quantum circuit that will be implemented on the quantum computer. They will give you the tool that will be able to solve this problem. So if you have, an algorithm that has a few qubit operations and 2 or 3 gates, logical gates, that's easy, anyone can do that. But once you get to real algorithms that have tens or hundreds of steps and logical gates or more, you really need a computer-aided design tool, and this is what Classic are doing. Another startup is Light Solver. This is a spin-off from the Weizmann Institute. And the idea here is a quantum annealer or quantum simulator based on a laser cavity. The idea here is that the laser cavity has a competition between optical modes until one of them wins, and this is the lasing mode. So you can show that this process inside a laser cavity is like an optimization problem. And their idea of Light Solver with some proprietary knowledge is to be able to map any optimization problems, for example, quantum chemistry or fintech or logistics and so on, to map it to the physical process that happens inside their cavity in a dedicated way in order to solve optimization problems very, very fast. So they already have a proof of concept and are starting to work with the market, both on the cloud service and also on the hardware itself. So this is LightSolver. Finally, I think the last example that I want to give is of a component manufacturer, and this is Raycol. So probably a lot of you know Raycol from nonlinear crystals for optics and photonics for many, many years, with the periodically poled KTP and the Piplin crystals. So now in the last few years, last couple of years, they have been moving more and more towards quantum applications. For example, generation of entangled photons for quantum cryptography, but also you see their components or crystals in quantum sensing and quantum imaging projects. For example, these images that you see below on the right are from a Fraunhofer project in Germany that is used their crystals, and they're rapidly growing in the demand that they see for these crystals. And this is an interesting example of some company that did not grow in quantum. They did not imagine themselves working specifically on that, but they have seen the potential and the demand, and they're moving more and more into that. And this is something that I think is very good for enlarging the ecosystem of companies in the world and in Israel. And of course, all of these companies rely on the engineering task force. You cannot rely only on physicists coming with PhDs from academia. And so this is very important, I think, for people in the audience here today. So the last part of the talk that I think that I still have a little bit of time to speak about is the national initiative. So as I said, this is a Telem Forum project, and really it's important for me to acknowledge and give credit to all my partners in the Innovation Authority, in the Council of Higher Education, in the Ministry of Defense, in the Ministry of Science, and the Ministry of Finance that have joined forces here. Usually Telem projects like the ones listed here, for example, the Israeli Center for Advanced Photonics that probably most of you know, are ad hoc infrastructure projects. And here in the Quantum Initiative, we have looked beyond only physical infrastructure. We certainly have that, but we are also looking at other components as we'll see in a few slides. Before that, a few main conclusions in the committee that was headed by Dr. Ona Berry and had experts from academia, from industry, from defense, both from Israel and consultations from abroad. So we got to a few main conclusions and identified a few main challenges. So I'll go over them briefly. First of all, we understood that quantum science and technology is a strategic field. It's only beginning now, and it will go for a long time. And Israel, that has a long time heritage in information communication technology and in cyber technology and in AI, this is like a natural evolution of the field that Israel should be position itself as a leader. Secondly, we understood that this is a change of paradigm. It's not like more of the same. A quantum computer is a whole different story. It's not like moving from CPUs to GPUs. This is something totally different. And the important understanding from that is that we need to develop an ecosystem that is relevant to this paradigm change. We have to enhance the relevant disciplines. We have to enhance the interdisciplinary approach or the multidisciplinary approach. And you'll see that in the components that I'll show in a couple of slides. Third, Israel's quantum science technology is only in its infancy. We are just beginning, and we need to have a long-term vision. So the focus of the first 5 years of the initiatives that we have initiated now is focusing on the main challenge of mostly human capital, as I'll explain in a second. And a lot of it is in research, but we see that as a part of a longer-term approach that will go on for many more years to come. And I hope that Israel will be smart enough to support this for a long time. The issue or the main challenge that we've seen from the, as you saw before, is that the community is small. It's very good, but it's small. For those who know the Chamishiya Kamarit, it's always funny to say that. And a lot of the components that we have here are dealing with enlarging and improving the community, while maintaining the best scientific and technological excellence level. A few other things, of course, the question of focus, we need to invest laterally because we don't know exactly what applications will come out, but on the other hand, we need to focus on some areas. So we had some discussions about that. International collaboration is interesting. Of course, we're not the only smart people on the planet. We have a lot of people to collaborate with, but also we noted that there is a window of opportunity for collaboration in quantum science and technology that is getting narrower and narrower as the field evolves and matures. So for example, already today in quantum sensing, we see that technology is already limited from the US for export, and not only from the US, also from the UK and other places. And we also know that there's a declaration from the US that they are going to apply restrictions also in the fields of quantum information and cryptography. It still has not come into place, but it's something that they have already declared that they have to do. And not only that, we also have a declaration from the last few months. The president of China even expressed some strategic declaration about that, that China will limit exports from within China to the world of quantum information application in some senses. And this is something that, you know, is counterintuitive to what we usually see from China. So there's an important emphasis to collaborate internationally while we still can, and typically with people that are our friends and are similar to us in size and so on. Finally, a point about management. We did not want to have a big, heavy management organization, and so we decided on a fast, flexible, fast in government, Israel government terms, management structure, and everything goes through the Telem partners. So they go through, you know, consortia in the Innovation Authority, or through the Israel Science Foundation through the academia, or through Mafat projects and so on, in order to have most of the money, as much as possible, going to the people that are actually doing the work and not on management stuff. And so from that, we got to 3 high-level goals that are pretty trivial: to advance the research community, to build an applied research and industrial ecosystem, and to bring more industry and more engineering into this area. And I think most importantly is to understand that this project or this initiative that is very much in R&D is not oriented to R&D. It's oriented to bring more jobs, to create more jobs, to create more economic boost or impact on the Israeli economy, to really implement quantum science and technology, and not just to have, you know, a hobby for people working in the lab. The rationale, I think I covered most of it: competitive and excellence. The initiative is open for almost totally unclassified, although Mafat is part of it, and so on. So gearing up to the end of my presentation, these are the components of the national initiative. The size of the program is about 1.25 billion shekels over the next 5 years. And you have some lateral components. So for example, the Direct Academic Research Fund, that is a collaboration that started, this is the first one that started from this initiative, is a collaboration between VATAT, the Council of Higher Education, and Mafat and the Ministry of Defense. So this fund does not have preference for quantum sensing or quantum communication or quantum computing. It goes strictly by scientific and technological excellence. And actually right now, at this very minute, there is the second round in the call for proposals for this Direct Academic Research Fund, relevant to academic partners, but also they have some capability to join forces with non-academic partners as collaborating entities or subcontractors, according to the Israel Science Foundation regulations. So this call will be open until the end of the year, or I think the first week of January. So your people that are relevant, I really encourage you to go and find details about this academic research fund. So this is one component. Another lateral component is human capital. This is a big title, and under it we have a plethora of activities, from opening tens of new positions in academia for academic staff, fellowships for PhD students, for postdocs, education programs and courses, both inside the academia and also from the industry side, workshops and courses that we'll initiate, student projects that will be done in the industry, and so on and so forth. This is the main effort in the program. Of course, we have the physical infrastructure part. Similarly, if you'd like, to the nanotechnology initiative that went on for 10 years and built really big infrastructure for the nano. So we're going to do similar stuff for quantum. We already initiated a little bit of that this year, but the main thing is yet to come. We have some funds for international collaboration, and the idea here is not to replace all the existing international collaboration platforms, but just to give them a boost in the quantum direction. And we also have a few focus areas. One focus area is projects in quantum sensing. This is applied for the industry based on the fact that we already have a well-established quantum sensing industry in the last 10 years in Israel. So we just need to enlarge it and give it a push to be able to compete in the world market. Quantum key distribution is an interesting example. We initially thought, well, you know, there's no industry in it. We'll keep it at the research level, but we already saw in the last year a tremendous change with more and more industries going into quantum key distribution in Israel. And we decided to enlarge this. So actually this circle, in principle, I didn't say that the size of the circle is relatively or roughly relative to the budget size of the whole program. So initially we thought of allocating quite small funds for quantum key distribution, but because of the change, the rapid change of the market, we decided to enlarge this. So actually this circle needs to be enlarged, and we have approved another industrial consortium like we have in quantum sensing that was, I think, mentioned by Shlomo, that's already been active for a year. We recently approved in the Innovation Authority another industrial consortium in quantum key distribution that will probably start working in about 2 months from now. And finally, the last focus area that we have is in quantum computing. The motivation there is not that we have a very substantiated industry at all. We have very small community, really a handful of people that actually know the business of quantum computing in Israel, but the impact is tremendous. And we understood that we in Israel, we have to be there in order to be relevant. So we're not conquering the whole world in the next 5 years. We're not aiming to beat the giants like IBM or Google or Intel or Microsoft, but we do need to be there and be relevant enough. So we have activity using the state-of-the-art quantum computers over the cloud, like IBM has was mentioned before, but IBM are not alone in this arena. Also, Microsoft are getting into this, Amazon are getting into this, and also our small vendors. We will have investment in academia and quantum computing in a dedicated way in order to generate more people into the pipeline of this field. And also we'll have a very substantial effort in applied quantum computing to put really a capability of quantum computing in Israel. It's written here that it's hardware, but we understand that all of the quantum computing stack, from the hardware through the control, compilers, and software, they're very intimately connected together. You cannot really differentiate or separate between them yet. So although it's written here hardware, it's probably going to be more than that. So this is something that we hope to be able to push during the next year. It's a very complicated component. And also we have ideas about forming a hub for new startups in this field to grow alongside the applied quantum computing efforts. This is roughly the national initiative components. So to summarize, quantum science and technology is not more of the same. It's a revolution, it's paradigm changing, and it's not only quantum computing that you hear a lot about, it's also quantum sensing, it's also cryptography or communication, and it's happening fast. It's happening fast around the world. It's happening fast in Israel, despite the very tough economic situation that the world and Israel also is part of in the last year. As I mentioned before, Germany has recognized quantum science and technology as one of the emerging technologies for the next few years. And also our initiative finally got the final approval in the government within the understanding of the high-tech investments in order to boost the economy. And also we see that people are not waiting for the government. The governments are always slow. Although I spoke pretty quickly here, governments are slow and the industries are not waiting. They're running fast. You see more and more VCs investing in startups and growing very quickly. So it's not only government. And finally, I think that it's very important for us to have initiatives like Photonics Israel to bring the engineering community closer to this field, or bring this field closer to the engineering community, to have additional players, to have additional partners, to bring and understand the requirements of quantum engineering. And we already see some of the universities offering courses or tracks in quantum engineering, both in the world and also in Israel. And this is something that I hope will manage to grow and evolve in the next few years. So with that, I thank you for your time, and I welcome if there are any questions in the chat.
Hello, thank you very much for your very excellent lecture. Engineers, the human capital bullet is a call for you to step in. So next week we have one more lecture. So I'm glad to see you all here. And now it's time for your questions. Please, Tal, can you see the Q&A?
Yeah, I can see some of them. So the first one that I saw, yeah, so I'll answer the question by Roy in a second, but just to answer Tzlil there from ISERD, of course, ISERD, we're working together. We're a part of the Quantera program, working with Danny Secker. We're in touch. So yeah, give me a call and we can talk. So Roy asked the question of this is being a small industry, how do we grow it? So that's an excellent question, and thank you. And of course, yes, this is a goal for the Israel National Quantum Initiative, certainly. And it goes through many ways. So I'll go back to the slide of the components. So growing the industry goes first and foremost, I think, through training people. Training people can be done by boosting academic research, by boosting applied R&D projects, like in the Innovation Authority, like connecting internationally, and also by the direct training, be it through academia or through industrial workshops. So I said a few words about this. This is certainly a challenge, and also you cannot, just push a lot of money for training people, because you have to have some smart growing together with the industries. So when we initially formed the program, we saw very little industry, but already now we see that it's gaining fast, and we see that people are a scarce, resource. We're always looking for people, both in the academia, in the industries, small and large industries, also in the government. We need the good people, and we cannot right now beat the rate of recruitment of people. So certainly this is an important goal for us, and we are attacking it in a number of directions. So I hope I answered this question. Then there's a question about the government budget freeze. So does it affect the effort? So yes and no. We have initiated the program about a year ago with what budgets that were already, we managed to approve them within the different R&D agencies that are taking part. So we pushed that forward. I think we pushed over 25% of the program already in terms of budget allocation. By now, maybe even more than that. And we got the final approval, as I said before, in the summer of 2020, through one of these, COVID-19 economy boost packages that was approved by the government. Right now, all of the program is fully approved, and we can go as fast as we can just make it. On the other hand, the budget freeze on the day-to-day basis, you know, it goes through the regular platforms, and everything needs to go through approvals and, you know, special committees to do that. This is part of the challenge. But right now, we're quite happy with the rate that we're pushing the effort forward. Yeah, so there's another question about getting the presentation. So I think that all of this is being recorded and will be uploaded to the AEAI website. And of course, you can ping me or through Shlomo, contact me for anything. Yeah, so these are the questions that I see, but if there are other questions, if we have time, I'll be happy to answer them as well.
Well, I propose that additional question will be sent to me, to Shlomo Glaser at Gmail, and you can find my address also in the LinkedIn. And I would like to thank you very much, Tal. It was a very good one, and I see the response of the people. So thank you again.
Sure,
and,
it was my pleasure. Thank you for having me. And it's very important for us, as you noted in the beginning, to have an open dialogue with the community, to understand where the community thinks we need to go. So please feel free to contact us, to ask follow-ups and to understand more deeply than the overview. I'll be happy to talk to anyone. Thank you very much.
All right. Thank you. Thank you to the audience as well.
All right. Goodbye.
Goodbye.